In this video, I want to look at why we make students take both Math 163, our computer lab course based on Mathematica, as well as Math 161, our Calculus 1 course, because students often wonder why we make you do this. The first thing that I want to say is that Mathematica is a state-of-the-art program that does all kinds of difficult computational tasks so that you don't have to do them by hand. Because it is a very complex program, there is a learning curve. But it turns out that if you spend just a little bit of time, you'll learn that Mathematica can simplify the task of doing a lot of your daily homework in math courses by taking the grunt work out of doing a lot of particular kinds of different sorts of calculations. So, for example, a lot of math courses require you to do algebraic manipulation of all kinds of expressions, things like factoring. So if we want to factor x to the fifth minus 16x cubed plus x squared minus 16, if you try and do that by hand, that's not an easy problem. But if I want to do it in Mathematica, Mathematica can factor it lickety-split. What if I wanted to factor x to the 6 plus 1? Again, Mathematica can factor it instantaneously. Well, what if I want to factor something like this polynomial? X to the sixth plus 2x to the fourth plus 3x cubed plus 4x squared plus 5x plus 6. Well, I feed that to Mathematica's factor command, and this time Mathematica spits the same thing back out. What this tells me is that Mathematica knows that this particular polynomial cannot be factored over the rational numbers using ordinary factoring techniques. And that's the consequence of a major theorem that you will learn something about when you take Math 301, our abstract algebra course. Another part of algebraic manipulation is expanding expressions. Suppose you wanted to multiply these two polynomials together. Now, multiplying binomials by other binomials is not difficult, but as soon as you start trying to multiply longer polynomials by other polynomials, it gets tricky and tedious to do it by hand. Mathematica, however, can give you the answer almost instantaneously. And so that's another thing that you might find useful in using Mathematica on your daily homework. Adding rational fractions. If you wanted to add this particular expression to this particular expression, the process by hand is to first of all find a common denominator and then multiply the numerators by the appropriate things and then add everything together and then simplify. Well, it's easier to do it in Mathematica. And you'll notice that Mathematica spits out an answer where the denominator is factored, and this denominator just happens to be the least common denominator of these two denominators. Much of calculus, we spend time working with specific functions, and there are all kinds of things that we do with those functions. So for the rest of this notebook, I want to look at the function f of x is equal to x squared times the sine of x cubed. In order to work with it in Mathematica and not have to retype the function's formula over and over, I can define it as a function. Now, this cell did not give me any output, but you'll notice that it does say that I did give that to Mathematica. One of the actual Lab 1 notebooks will talk a lot more in detail about that. Well, what kinds of things do we typically do with functions? Well, one thing is we evaluate functions at specific points. That's easy in Mathematica. We also often create tables of values, particularly with calculators. Now, in this table of values, for every one of these entries, the first coordinate is the x value, and the second coordinate is f of that particular x value. Of course, this is kind of an ugly-looking table. Well, we can fix that up easily enough. And by adding a table form command around that, we get a nice two-column table where the first column is the x value and the second column is the y value. And that's just like your calculator tables of values. What else do we do? Well, we plot functions a lot. Now, one of the nice things about Mathematicus functions is that when you plot them, you get much nicer graphs than you get on a graphing calculator. Among other things, both axes have a scale, and Mathematica will pick an appropriate y scale to show you the details of the function over the x range that you are plotting. Now, in this particular plot, we can see that there's some kind of a root here at, let's see, this is 1, that's 1.2, this is 1.4. There's a root somewhere between 1.4 and 1.6. There's a local max a little bit past 1.2, and there's some kind of local min down here. Looks like it's between 1.6 and 1.8. And one of the things that we study in calculus is how to find those particular sorts of things on a graph. Well, it turns out that Mathematica can do all of those particular tasks. To find this root that is a little bit past 1.4, we can use this syntax. And when we do, the root, this is telling us that that root is located at 1.46459. Now, this is actually a decimal approximation, but it is a decimal approximation that is accurate to 5 decimal places. If I want to find this maximum, well, that maximum is between 1 and 1.5, and the syntax for having Mathematica find a maximum looks like this. We're not going to look at exactly what this is saying in this particular notebook. I just want to convince you that Mathematica can find the maximum. And when I ask Mathematica to do this command, Mathematica tells me that that local max is located at x is equal to 1.2410, and the y value, the local maximum value for the function, is 1.45171. Local minimums are done in the same way. This local minimum is between 1.5 and 2. So if I ask Mathematica to minimize the function between 1.5 and 2, this is what I get. The minimum occurs when x is equal to 1.69259, and the minimum value is actually equal to minus 2.83816. Well, let's think what else you do in calculus. You spend a lot of time learning how to take limits. Mathematica has a limit command. This output is the exact value of the limit of f of x as x goes to pi over 4. Now, that's not a very meaningful expression because I know I don't know what the sine of pi cubed over 64 is. But Mathematica has a built-in change stuff to a numeric approximation command called the capital N command. And when I hang that around the limit, I get that that limit's value is 0.287293. In Calculus 1, we spend a lot of time learning how to take derivatives. Well, Mathematica knows all about derivatives. The function that we're looking at requires the product rule. And if I ask Mathematica to differentiate the function using Newton's prime notation, it calculates the correct derivative. If I look at asking Mathematica to find the derivative using Mathematica's version of Leibniz notation, same thing, it knows the product rule and it can calculate the derivative correctly. If we want to evaluate the derivative at a particular value, the prime notation is easier because all I have to do is put the number into the prime notation. Again, this is an exact value. I can hang a capital N around that to get the decimal equivalent. Part of Calculus 1 is learning that the derivative at a point is the slope of the tangent line. We can make Mathematica draw tangent lines. So this is the picture of the function with its tangent at x is equal to 1. Again, I'm not going to worry about trying to figure out all of the details in the input cell in this demonstration notebook. But one of the points in Calculus 1 is that as you zoom in other words, you look closer and closer and closer to just around the stuff around x is equal to 1, the tangent line and the function become indistinguishable. Well, we can make Mathematica do that if we want to in a series of cells. And so by the time we are looking at an x range of 0.99 to 1.01, we really can't tell the tangent line and the function apart because there's really only one line. Finally, I want to say something about Calculus 2. Calculus 2 at Buff State is the study of integration, and Mathematica knows how to integrate things. If I want just an indefinite integral, an antiderivative, and there is something called a closed form for the indefinite integral, Mathematica can find it. In this case, Mathematica is doing a U substitution. If we have a definite integral, we can have Mathematica find the exact value of the definite integral. The capital N trick works, of course, for turning that mysterious, nonsensical exact value into a decimal equivalent. So this particular definite integral here has a value that is approximately 0.153233. It's best, though, to use what's called the inintegrate command because it will work even if we don't have a closed form, and you'll notice that it gives the same answer. That gives you a whirlwind tour of the kinds of things that Mathematica can do for you in a calculus course. And in my calculus class, once you get your feel for doing Mathematica, you should feel free to use Mathematica to do all of the plotting and any kind of algebraic simplification and things like that that you want to in your daily homework.